We're going to continue on with our calculus review, our series review. This is video number 3. So the first one that I want to do here is sigma n equals 1 to infinity of n squared over n factorial. So this one is similar to one that we did before, but and when we did it, I said anytime we see a factorial, ratio test is generally going to work pretty well. So L equals limit as n goes to infinity, absolute value. Remember, I always write a sub n plus 1 over a sub n because that can often get me points for showing some work. So we will go ahead and put our pieces in. This is the limit as n goes to infinity, absolute value. All right, so a sub n plus 1 is going to give me n plus 1 squared over n plus 1 factorial. And then I'm going to copy dot flip, so we're going to multiply reciprocal. We went over that a little bit earlier. I'm going to get n factorial over n squared. Now, again, I always like to reorder these a little bit. Limit as n goes to infinity, absolute value. I'm going to put the squared terms first, so I'm going to write n plus 1 squared over n squared times n factorial over n plus 1 factorial. Now, how do things cancel? Well, this whole limit here, this piece of the limit is equal to 1. And that's because I got an n squared polynomial versus an n squared polynomial. Lots of logic and reasoning for that, but we're not going to go into it. Should be okay with that. And then this one right here works in the same way as the one that earlier did. This piece right here, just all of those cancel with all of the factorials and leave me with just the n plus 1. So this is equal to the limit as n goes to infinity, absolute value. I just get 1 over, actually what I often write is 1 times 1 over n plus 1, which is the limit as n goes to infinity of just a 1 over n plus 1. All right, what happens to that? It is 0, which is less than 1. So therefore, converges by ratio test. Now, one thing I'll say, and I say this a lot, it's like if you don't know what to do on a series question, a lot of times the ratio test will work. There were some examples earlier in my videos above, or the earlier videos, where it was like you could do the ratio test and it would work. It would just take more effort. So if you're at a loss, trying ratio test is always worth giving it a shot. All right, so let's do the next problem. What we're going to do now is do some series that have x's in them. All of them so far have just had n's. So the directions for this one are going to be find, and I guess directions for all the previous ones were converge or diverge in y. So this one is a little bit different. I want to find the radius of convergence. So the thing we want to do it for is sigma n equals 1 to infinity of, I'm going to take a fraction bar. In the top, I'm going to put x minus 3 to the n. And in the bottom, I'm going to put a 4 to the n. There's a handful of different ways to do this one. I'm going to use the ratio test because it's the easiest, most automatic. So I'll give you a reminder. Radius of a circle is half the diameter. Radius of convergence is half the length of the interval. I'll say that again, and when we get down a little bit further, we're just looking to go half the length of the interval. So let's set up our ratio test. L equals limit as n goes to infinity, absolute value. Remember, always write this. A sub n plus 1 is going to be x minus 3 to the n plus 1 over 4 to the n plus 1. Copy dot flip, I'm going to get 4 to the n over x minus 3 to the n. And then we're going to go ahead and rewrite our limit as n goes to infinity. Absolute value. I'm going to reorder them like I have previously. You might not need to do this. X minus 3 to the n plus 1 over x minus 3 to the n times 4 to the n over 4 to the n plus 1. What cancels? All of these with all but the last of those. You know what I could do? I could go and cross that out. All of the up to the n cancel with all of up to the n there and leave it with just one power in the top. And then all of these cancel with all of those except for the one in the bottom. So what do we end up getting? The limit as n goes to infinity. Absolute value, x minus 3 over 4. What I want you to see, there's no n's. So the limit as n goes to infinity of this thing, well, it is just that thing. Because there's no n's anymore. So it's not going to change as n goes to infinity. It's just going to be what it is. And I want that less than 1. So what I have is x minus 3 over 4, absolute value, less than 1. And then you should know, what do we do? Take negative 1, less than the inner thing, which is x minus 3 over 4, and then less than 1. So algebraically, I just need to solve for my x or get my x isolated. Going to multiply everything by 4. We treat it like a double equal sign, sort of. That gives me negative 4 less than x minus 3 less than a positive 4. And now I'm going to add 3 to everything. When I add 3 to the left, I get negative 1 less than x. When I add 3 to that one, I get 7. So this would be like the interval of convergence without checking the endpoints, and we'll talk about that in a little bit later. But what I want to point out here is that, look, this interval goes from negative 1 all the way up to 7. What's that full length? Well, it would be 7 minus the negative 1, or you might just be able to see that that full length is 8. Remember, the radius of a circle is half the length of the diameter, or half the diameter. The radius of convergence is half the length of the interval. Well, the length of the interval is 8, so half of that is 4. So the radius of convergence for this one is 4. Now, there's some definite shortcuts to get there, and you may see some of those. Notice it is just this number here. That's not always going to be the case, but it sometimes is. And hopefully you're okay with some of the recognizing those patterns. And hopefully you also understand what the radius of convergence is. All right, let's do the next one. I'm going to ask you for an interval on this one. So our next problem, we want to find the interval of convergence for this series here. What do we do for the interval of convergence? You should know. We use the ratio test. So L equals, L equals the limit as n goes to infinity, absolute value, a sub n plus 1 over a sub n, which is the limit as n goes to infinity, absolute value. I'm going to take x plus 5, raise it to the n plus 1, and put it over top of n plus 1 times 2 to the n plus 1. Copy dot flip n times 2 to the n over x plus 5 to the n. I'll go ahead and reorder. Equals limit as n goes to infinity, absolute value, x plus 5 to the n plus 1 over x plus 5 to the n times 2. I'll do the other ones first. I'm going to go n over n plus 1 times 2 to the n over 2 to the n plus 1. Now, what cancels here? This limit is equal to 1 because they're polynomials of equal degree. All of those cancel with all of those, except for 1 that's left over at the end. And same thing here. All of these will cancel with everything but with one of those. So when I reorganize, I get limit as n goes to infinity, absolute value, x plus 5 over 2. Those are the only surviving pieces. So again, there's no n's anymore. So I want this less than 1 because that's what the ratio test tells me. So I write negative 1 less than x plus 5 over 2 less than 1. I'm going to multiply negative 2 less than x plus 5 less than 2. And then I'm going to subtract 5, negative 7 less than x less than negative 3. So that's an interval. What I need to do is check the endpoints of this interval. So we'll go ahead and do that over to the right. X equals negative 7 and x equals negative 3. To be honest, a lot of times I like to do the x equals negative 3 first, but I'm going to go ahead and do the x equals negative 7 first. What I do is I write sigma n equals 1 to infinity, and I just plug in the x value of negative 7 right here. That gives me negative 7 plus 5 to the n over n times 2 to the n. Well, that simplifies down to sigma n equals 1 to infinity of, I get negative 2 to the n over n times 2 to the n. And you should see that I've got 2 to the n twice. I just got to take care of that little negative. This is sigma n equals 1 to infinity of negative 1 to the n times 2 to the n over n times 2 to the n. Notice those cancel. This gives me sigma n equals 1 to infinity of negative 1 to the n over n. Now, this one, we've done ones that are similar to this. This thing is alternating, and the limit of the non-alternating piece is 0. So this thing converges by AST. This happens very frequently when we're doing endpoints. Not all the time, but frequently it does. So we get that alternating series test. For the next one, for the next endpoint, so we're done with the x equals negative 7. Now we got to check the x equals negative 3. So we do the same thing. Sigma n equals 1 to infinity of, change the x. I'll zoom out a little bit so you can see that other piece. I'm just changing this right here to a negative 3. So negative 3 plus 5 to the n, that's a parenthesis, over n times 2 to the n. Now this one actually works out a little bit easier. This is sigma n equals 1 to infinity of, it just simplifies down to 2 to the n in the top over n times 2 to the n. And again, these cancel. And that gives me sigma n equals 1 to infinity of just 1 over n. Now, this one is a p-series with a p-value of 1. So this one diverges by p-series because p equals 1 is less than or equal to 1. So what do we get? This one diverges. This one converges. So what I do is I copy this interval right here. I write negative 7. I'm going to leave a gap. X, and then negative 3. And this one stays at less than, because I do not want to include the negative 3, because this is the interval of convergence, and at negative 3 it diverges. But at negative 7, this series converges. So what I do is I write less than or equal to say that all x's including that negative 7, or all x's in that interval including that negative 7 converge. So this is the interval of convergence, and it's a good demo of when we have one that converges and one that diverges, and we use the alternating series test. Hopefully you're good. We'll keep going in video number 4.